Hello everybody and welcome to our video on sequences. So we've got a whole lot to cover here, but let's just start with the definition. So a sequence is a function whose domain is the set of positive integers, and this sometimes includes 0. So the domain, what we're saying here, is usually the set 1, 2, 3, so forth and so on. But sometimes we will also include 0. Now, when we talk about sequences, we, instead of writing f of n for our function notation, we will usually denote sequences as a sub n. And we often think of sequences as lists. For this class, we will focus on the more interesting case of infinite sequences, so not just finite sequences, but sequences that have infinitely many terms. Now, we're going to take a look at a few different notations and some basic examples in a moment. So the following notations are equivalent. So bracket A1, A2, A3, dot, dot, dot. That you can list out a sequence like that. You can have closed brackets with the formula in terms of n for a sub n. Or you can have that same closed bracket with your formula a sub n that specifies n from which value to infinity. Usually, again, we go with n equals 1, but you may want to specify that you're only considering a list starting at n equals 3, for example. Okay, so another quick definition. A sequence is said to be defined explicitly if the general term a sub n can be given as a formula of n. So let's look at some examples of explicit sequences. So I've written these a couple different ways. So we've got bracket n over n plus 1 from n equals 1 to infinity. So we can write our formula a sub n equals n over n plus 1, or we can list out the terms. How do I get these terms? I just plug in the numbers. When n is 1, what do I get? 1 over 1 plus 1, that's 1/2. When n is 2, I get 2 over 2 plus 1, that's 2/3, so forth and so on. Now for part B here, we've got a sequence with alternating terms, -1 to the nth power times n plus 1 over 3 to the n. So the key to recognizing this pattern here, just as a little aside, this -1 to the n part. When n is 1, -1 to the nth power gives me -1 to the first power, which is -1. If n is 2, I get +1, -1 squared is +1. N is 3, I get -1 to the third power, which is -1, and so forth and so on. So if I just have this expression on its own, this gives me a sequence that alternates between -1 and 1. While we're on the topic, we'll note that similarly, if I had -1 to the n plus 1 power, I would get the same kind of sequence, except it would start with +1 and alternate to negative, positive, negative, so forth and so on. Okay, so we look here, we've got this term that's alternating the terms between -1 and +1, and then n plus 1 over 3n. So we start plugging in values for n. When n is 1, what do I get? I get -1 times 2 over 3 to the first power, that's -2/3. When n is 2, what do I get? I get 1 times 3 over 9, so forth and so on. Okay, so I'm going to go ahead and skip going through every single term here, but just go through, check, plug in a few values for n, make sure that what you see here in the expression makes sense. So now we want to find a formula for the general term a sub n of this sequence. 1, -1/3, 1/9, -1 over 27, 1 over 81, so forth and so on. And basically this kind of stuff generally boils down to pattern recognition. At least with a lot of these, that's the easiest way to do it. So first thing I'm going to go is, hey, all these other terms are fractions, so I'm going to write my first term as 1 over 1 to make the pattern a little bit easier to figure out. And then what do I notice? I notice that the numerator of this fraction is alternating between 1 and -1. And so I can use an expression like -1 to the n plus 1th power. And then my denominator, well, that's a little tricky. I've got 1, 3, 9, 27, 81, so forth and so on. What I should notice is what's happening every time here is multiplying by 3. And repeated multiplication means an exponent with the base 3. So this should be like 3 to the power of n, except when n is 1, I should get 1. So I have to take 1 away, so I get 3 to the 0 power when n equals 1. Now, of course, you can plug in some values for n to double check that this is right, but this is our formula. All right, so let's move on. So another definition, a sequence is said to be defined recursively if its initial term or terms is or are given explicitly and the nth term is expressed in relation to previous terms. So we'll just take a look at what the Fibonacci sequence looks like. It's defined recursively by the conditions f1 equals 1, f sub 2 equals 1, f sub n equals f sub n minus 1 plus f sub n minus 2 for all n greater than or equal to 3. So we'll just start out by listing the third term, f3. So this formula says if n is 3, then n minus 1 is 2, and n minus 2 is 1. So f sub 3 is f sub 2 plus f sub 1, and we already have those two values. 1 plus 1 is 2. So then if I wanted to compute f sub 4, I'm going to be taking f sub 3 plus f sub 2. And we computed f sub 3 is 2 plus f sub 2, which was 1, and 2 plus 1 is 3. And the fifth term will be the fourth term plus the third term. So that's 3 plus 2, which is 5, and so forth and so on. So if I try to list these terms out, I get 1, 1, 2, 3, 5. And I know each term is just adding the previous two terms together. So 5 and 3 is 8, and 8 and 5 is 13, and so forth and so on. All right, that's it for example 2. So let's move on. Graph a sub n equals n over n plus 1. So I'm going to start by just plugging in some values. Again, we're assuming that we start with n equals 1 here. If a problem says otherwise, you would start with n equals 0, but we get 1 over 2. A sub 2, I plug in 2, I get 2/3. A sub 3, I plug in 3, I get 3/4. A sub 4 is 4/5, and so forth and so on. Okay, so now we want to graph it, and the graph's not really going to be to scale. We'll put 1 up here, and then 1, 2, 3, 4, and we'll tack on a 5 here. So when I plug in 1, I get 1/2. I plug in 2, I get 2/3. When I plug in 3, I'm going to get 3/4. And 4/5, and 5/6, and so on. And what I want to notice here is that the sequence has a bunch of terms that are going to get arbitrarily closer to 1 for their output values, but they're never quite going to reach it because, of course, this numerator here, n, is smaller than n plus 1. So the fraction's never going to be 1, but these values are getting arbitrarily close to 1. So you might think that you could state that the limit as n goes to infinity of n over n plus 1 is 1. And that would be correct. Now we have some techniques from Calculus 1 that we can use to compute this limit, and we'll come back to that. But for now, we're going to take a look at the informal definition for the limit of a sequence and the formal definition. So the informal definition of the limit is really just how you think about a limit intuitively. So we say that a sequence a sub n has the limit L, and we write the limit as n goes to infinity of a sub n equals L, or a sub n approaches L as n goes to infinity, if we can make the terms a sub n as close to L as we like by taking a sufficiently large value for n. If the limit as n goes to infinity of a sub n exists, we say that the sequence converges or is convergent. Otherwise, we say that the sequence diverges or is divergent. So again, intuitively, what we're saying when we talk about a limit of a sequence is the terms get arbitrarily close to some fixed number, L, as long as we take big enough values of our input, n. But oftentimes, this intuitive definition is not good enough for us to work through the logic of certain problems, to show certain things rigorously. So we have developed a much more precise definition for the limit, and that is as follows. A sequence a sub n has the limit L, and we write the limit as n goes to infinity of a sub n equals L, or a sub n goes to L as n goes to infinity, if for every epsilon greater than 0, there is a corresponding integer n such that if little n is bigger than big N, the distance between the terms a sub n and L is less than epsilon. So you will probably recall that this is very similar to the definition for the limit from Calc 1, but that definition wasn't about sequence terms, it was about functions, more general functions. So we've rewritten this in terms of the language of the sequences. So let's recap this, what this says. For every epsilon greater than 0. So epsilon is a upper bound on distance. Really, epsilon is just a number, but in this expression, we're saying this is the upper bound on the distance, and this absolute value of a sub n minus L means the distance between the a sub n term and L. In particular, we mean on the y-axis. We're talking about the vertical distance, the distance between the outputs. So if we take a look at this picture, that's what we're trying to show here. So this highlighted space is the area of the graph whose distance from L is epsilon. And what we're saying, this sequence that we've graphed here, is you might have a sequence that's alternating like this, but as long as once you get to a certain n value, all of the terms fall within that epsilon, you've satisfied this inequality. But the key to the definition of the limit is that it has to be true for every epsilon greater than 0. Meaning that I can make this number epsilon smaller and smaller, and if I do, I might need to go to a bigger n value if I shrink down how much distance I'm allowing on either side of the limit, but I can always find that second n value, or third, or fourth, or so forth and so on. So typically, we use this definition to do the heavy lifting for dealing with concepts involving limits. And we will use it to prove some things that are much easier tools to work with. So we have this this is like our sledgehammer for sequences. We bring this out when we've got something real heavy to knock down, but most of the time we prefer to use other tools that are a little easier to work with. But let's go ahead and look at an example of applying this definition to show that a sequence is divergent. So we have the sequence -1, 1, -1, 1, -1, 1, so forth and so on. So the general term for this sequence looks like -1 to the nth power. And we want to show that this sequence diverges. Now, graphically, this sequence is pretty easy to understand. It just alternates between -1, 1, -1, 1, so forth and so on. So if we want to use the definition to show that this is divergent, to rigorously show it's divergent, even though it's intuitive, we look at the graph and it's pretty clear that it's not approaching any one fixed value. If we want to actually show this rigorously, well, what do we do? Well, what we're going to do is assume that the sequence converges and then show that we reach an impossibility. In other words, a contradiction. So let's go for it. We're going to assume that the limit exists and is L. So we're assuming that the limit exists and takes some value L. Now, I don't know what L is. You know, if we look at the picture, we could imagine maybe L is like this value here. Now, if that limit exists, that implies that for any epsilon greater than 0, there is an n such that the absolute value of a sub n minus L is less than epsilon for all n greater than big N. Okay, so now what I'm going to do is pick a specific epsilon. So if I want to show that something isn't true, that something breaks apart, all I need is one counterexample, and that's the key here. If I was trying to show that this sequence converged, I'd have to show that it converged for all epsilon, but I'm actually trying to show it diverges, so I just have to find one epsilon where things fall apart. So I'm going to pick epsilon equal to 1/2. Now, as far as what epsilon you pick, that's a really frequent question students ask. There is no hard and fast rule for which epsilon to pick. I picked this epsilon because I figured any point that I pick in this interval, if I go out 1/2 in either direction, there's no way that I'm going to catch every term of the sequence that distance away, no matter what I tried to pick for L. I could have also picked epsilon equals to 1. That's the largest value you could pick and make it work out, but it gets a little messy in that particular case due to some algebra stuff. So epsilon equals 1/2 is just going to be a little bit cleaner to work with. Okay, so if epsilon is 1/2, then a sub n minus L should be less than 1/2. But, and I should say for any n greater than n. But we will choose some specific points to plug into the sequence. So we're going to choose in this case, what do I know is happening? -1 to the nth power, it's alternating. So anytime n is an even number, I get a +1, and when it's an odd number, I get a -1. So I'm going to choose k greater than n, where k is even. Then that implies that a sub k minus L is equal to 1 minus L. And if this limit exists, this should be less than 1/2. Okay, so I have an inequality with an absolute value. So the way I solve that is I set 1 minus L between positive 1/2 and negative 1/2. I subtract 1 from both sides here. I get negative 3/2 is less than negative L is less than negative 1/2. And if I multiply everything by negative 1, I have to flip my inequality around. And so I get L is between 3/2 and 1/2. But this also implies that A sub k plus 1, right? If k is an even number, k plus 1 is an odd number. So my A to the k plus 1 term is going to be negative 1. So this will be negative 1 minus L. This should also be less than 1/2, which implies negative 1 minus L is between negative 1/2 and 1/2. I add 1 to both sides of the equation this time. So I get negative L is between positive 1/2 and 3/2. Now if I multiply by a negative 1, I get L is between negative 1/2 and negative 3/2. So I have two conditions on L. So I've marked the first one star and the second one double star. And the first condition says, well, based on what we just did, L must be between 1/2 and 3/2. But I also just showed that L must be between negative 3/2 and negative 1/2. But these intervals don't overlap, so that's not possible. So star and double star are a contradiction. Okay, well, what does that mean? That means that everything I said here was true, except for the one assumption that I made without evidence, which was this. I assumed that the limit existed and was equal to L, and since that resulted in an impossible situation, that implies that the limit, as n goes to infinity, of negative 1 to the nth power does not exist. Okay, well, that's a fairly challenging problem, and that's, to be honest, about as tough as it gets. We just need to understand how to use this definition so that we can work our way through the tougher things so that the easier problems won't be so much trouble. Okay, so now we'll move on to a useful theorem. So this theorem says if n is approaching infinity, oh, that should say x. Typo. Okay, let me fix that real quick. Okay. If we take the limit as x approaches infinity of f of x, and that's equal to L, and f of n is equal to a sub n, where n is an integer, then the limit as n goes to infinity of a sub n is also L. So there's a lot of notation here, so it can kind of trip you up a little bit. But let's think about what we're trying to say here. Here, this f of x is a function whose domain is at least 1 to infinity. Whereas a sub n, its domain is only the integers. So what we're saying here is, if I have a function that's equal to the sequence on all of the integers, then that function, if it has a limit as x goes to infinity, its limit will be the same as the limit of the sequence. So if we look at this graph, the purple graph is our f of x, and all the red dots are the sequence points. And so what we're saying is, if those red dots are always landing on f of x and f of x levels off and approaches L, then that sequence has to approach the same thing. So because this sequence is following the function like a little lost dog, I call this the puppy dog theorem, mainly because it doesn't have a name as far as I've ever heard, and I refer to it a lot, so I got to give it a name. It comes up too often not to call it something. Okay, so moving on, let's do an example. Find the limit as n goes to infinity of ln of n over n. So I don't have any algebraic way to evaluate this limit, and the only tool that I could think of offhand, this might look like a L'Hopital's rule problem. But L'Hopital's rule doesn't apply to sequences because sequences aren't differentiable, right? Keep in mind, if we go back to some of our earlier graphs, sequences show up graphically as distinct points. There's no continuity and hence no differentiability. So sequences themselves are not differentiable. Neither are they continuous. So if I want to use L'Hopital's rule, I have to first consider a function that is differentiable. So we'll just consider f of x equal to ln of x over x. So we take the limit as x goes to infinity of this function. This has infinity over infinity indeterminate form. And so I can apply L'Hopital's rule. And this is equal to the limit as x goes to infinity of 1 over x over 1, which is 0. This implies that the limit as n goes to infinity of ln of n over n is also 0 by that puppy dog theorem. Now, oftentimes, I've been accused of being really picky about this particular requirement, converting this to a function of x instead of just leaving it in terms of n and trying to write L'Hopital's rule that way. And I'm picky for what I think is a very good reason, because not all sequences have real valued functions that you can swap them out with. Take, for example, n factorial. You're not going to find any sort of continuous differentiable function to replace it with. So what I'm trying to make sure that students do is actually go through the thought process to think, hey, is it even possible to find this real valued differentiable function that I can use to compute this limit with, say, L'Hopital's rule? So I always want students to make this extra check here to do that conversion. Go, does this really work? Does it make sense to convert the sequence this way? Okay, so now we're going to glance at a few limit laws for sequences. Now, I'm not going to spend much time on these because these are the same exact limit laws that you have for Calc 1. So if two sequences are convergent sequences and k is a constant, the following is true. The limit of the constant is just the constant. The limit of a constant multiple of a sub n is k times the limit as n goes to infinity of a sub n. You can split up limits on sums, on differences, on products. You can split them up on quotients as long as the limit of the denominator isn't 0. And you can also pull powers inside of a limit, outside of the limit, assuming that all the terms are positive. That is an important condition for the 7th property there. So these are the same standard properties that you had for limits with Calc 1, so nothing new there. Okay, so let's consider another theorem, the continuity and convergence theorem. This says that if the limit as n goes to infinity of a sub n is L and the function f is continuous at L, then the limit as n goes to infinity of f of a sub n equals f of the limit as n goes to infinity of a sub n, which is f of L. In other words, what this says is, if f is a continuous function, you can move the limit inside the function. That's what we're doing here. So if we take a look at example 6, we have the limit as n goes to infinity of cosine of 2 over n. So since cosine is continuous, that implies that the limit as n goes to infinity of cosine of 2 over n is the same thing as cosine of the limit as n goes to infinity of 2 over n. And since this limit goes to 0, this whole thing is cosine of 0, which is 1. All right, moving on to another example. So now we'll talk about the squeeze theorem for sequences. So the squeeze theorem for limits of real valued functions applies in the same way to sequences. So if you have a sequence B sub n that is bounded by two other sequences, A sub n and C sub n, and the limits of that A sub n and C sub n are both the same, equal to L, then the limit of that middle sequence, the one bounded by both, will also be L. So when we look at this, in green is our B sub n term on this graph. And what we're saying is this blue sequence and this purple sequence bound the green sequence on the outside, and the purple and blue sequences both have limits at L. So effectively, they are squeezing the terms from our green sequence between them and forcing it to also approach L. Okay, so now let's apply the squeeze theorem. Determine whether the sequence A sub n equal to n factorial over n to the n power converges. Okay, so what is A sub n? Well, n factorial means n times n minus 1 times n minus 2 times so forth and so on, 3 times 2 times 1. And n to the nth power means multiplying n by itself n times. So first thing I notice is I can cancel the n over n here. And the next thing I notice is that each pair of terms here, n minus 1 over n, n minus 2 over n, all of these pairs of terms are less than 1. And of course, if I multiply a bunch of stuff less than 1, then the result is less than 1. So this whole term is less than 1 times 1 over n. So I've left this 1 over n at the end. The whole thing is less than 1 over n. But also, all of these values for n are positive, so this whole thing is greater than 0. So now I have two sequences, the constant valued sequence 0 and the sequence 1 over n, and they bound my original term, A sub n. So the limit as n goes to infinity of 0 is just 0. And the limit as n goes to infinity of 1 over n is also 0. And that implies the limit as n goes to infinity of A sub n is 0 by the squeeze theorem. All right, well, that's it for that example. So now we're going to move on to a theorem that is a direct result of the squeeze theorem. So this theorem says if the limit as n goes to infinity of the absolute value of A sub n is 0, then the limit of the original sequence must have also been 0. Okay, so how do we prove this? We start by saying A sub n has to be between the positive and negative of its absolute values. So just as a little aside, that's like saying 3 is between the absolute value of 3 and the negative of its absolute value. Of course that's true. Likewise, negative 3 is between negative the absolute value of 3 and positive the absolute value of 3. So any term is between its negative absolute value and positive absolute value. And since the absolute value is going to 0, then the negative of that is also going to 0. And so both of the limits on the ends approach 0, and by the squeeze theorem, the limit as n goes to infinity of a sub n is also 0. Now, since this theorem is a direct result of the squeeze theorem, you could, in many cases, apply the squeeze theorem to problems that you can also solve with this theorem. But this theorem makes things a little bit simpler. See the following example. The limit as n goes to infinity of negative 1 to the nth power over n. Okay, so we're going to take the limit as n goes to infinity of the absolute value of this thing. And normally these terms alternate between positive and negative values. But since we're taking the absolute value, all of the terms are going to be made positive, which means I can eliminate that alternating negative 1 to the nth power term and just write 1 up top. And since n is approaching positive infinity, all of our n values are going to be positive. So this will be 0, and that implies that the limit as n goes to infinity of negative 1 to the nth power over n is also 0. And that's it. Next, evaluate the limit as n goes to infinity of n over n plus 1. Now, in my Calc 1 course, I cover a lot of examples of this type of limit. So this is one where we can just delve into algebraic techniques, but they all rely on the following fact, that the limit as n goes to infinity of 1 over n to a power is 0 as long as that power is positive. So my goal with these is always going to be to rewrite this limit in a way that I can use this identity. So for this example, or in general, how I'll do that is multiply by 1 over the highest power of my variable in the denominator. And the highest power of the denominator is 1, so I'll multiply by 1 over n on the top and bottom. And I get 1 over 1 plus 1 over n. And now I know this term 1 over n goes to 0. So this is going to be just 1. And while we're at it, I'll just make up a little bonus example here, because I didn't put many of these in here, and they're nice and quick. So we'll just throw a little bonus example. How about the limit as n goes to infinity of 3n over 5n squared plus 2. So in this case, the highest power of my denominator is 2, so I'll multiply by 1 over n squared on the top and bottom, and that gives me the limit as n goes to infinity of 3 over n up top over 5 plus 2 over n squared. So this term goes to 0, this term goes to 0, and all together we're left with 0 over 5, which is 0. So the thing I really want you to notice is that the approach that I'm taking, the reason I'm taking it is because it guarantees that I always end up with a constant value in the denominator. After that manipulation, you will sometimes see people use an approach of multiplying by 1 over the highest power in the numerator. But when you do that, it sometimes results in weird situations where it's harder to determine what the final limit is, just because the algebra works out a bit different. By always multiplying by 1 over the highest power of the denominator, you always get a constant in the denominator, and that makes things a lot easier to analyze. Okay, yeah, this section's pretty long. It's a real marathon, so we're going to keep going, keep up the pace. Fact, the sequence r to the n power is convergent if r is greater than -1 and less than or equal to 1, and divergent for all other values of r. In particular, the limit as n goes to infinity of r to the n is 0 if r is between -1 and 1 if r is 1. So let's go ahead and break this down and see why this is true. So when r is 1, it's pretty trivial. R to the n is 1 to the n, which is 1. So the limit as n goes to infinity of r to the n is just 1, the constant value. Okay, so that takes care of that. What about -1? So we've got that -1 case, r equals -1. That's -1 to the nth power, which we already showed diverged. Okay, so now we're going to deal with the case where r is not between 1 and -1. So if r was greater than 1, then I'm looking at r to the nth power, and I can think about the exponential function y equals a to the x power, where a is greater than 1. And if I think about that exponential function, I know that the exponential function, when x is 0, I get 1. When x is 1, I get a, which is bigger than 1. And I know that this graph is shaped like this. So I know that when r is greater than 1, I know that r sub n is going to approach infinity just like a to the x does. Now, if r is less than -1, that's a little bit trickier because we don't normally deal with negative bases. But what I'm going to think about is an exponential function where I have -1 times a to the x power. Then this becomes -1 to the x power times a to the x power. And this term, a to the x, is still going to approach infinity. So the limit of, as x goes to infinity, of the whole thing still does not exist. All right, we've got one term that just goes back and forth between 1 and -1, and the other term grows unbounded. So this limit is not going to approach any fixed number. Now that is a very quick explanation, not super rigorous. I'm not using an epsilon delta argument here. We're just not going to dig into that for this one. But now we've got our final case to consider. So we've got that it diverges when r is greater than 1, less than -1, and at -1. Okay, what about when r is between -1 and 1? Well, in this case, we can think of r like a fraction. Now, of course, it could be a decimal that isn't able to be written as a rational number, an integer divided by an integer. But if r is between -1 and 1, then r can be written as 1 over k, where k has an absolute value bigger than 1. It might be negative, but its magnitude is bigger than 1. And so r to the n can be thought of as 1 over k to the n. And since k to the n will go to infinity, that means the limit as n goes to infinity of r to the n will be 0. Okay, so kind of a lot to go through to make all that clear, but the big point here is that whenever I see a sequence of this form r to the n, I know if r is between -1 and 1, the limit is 0, and if r is 1, it's 1, and it diverges in any other case. Okay. Let's take a look at a few definitions. The definition, a sequence is called increasing if a sub n plus 1 is bigger than a sub n for all n greater than or equal to 1, meaning a2 is bigger than a1, a3 is bigger than a2, so forth and so on. It's called decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. That is, a2 is less than a1, a3 is less than a2, so forth and so on. And if a sequence is either increasing or decreasing, then it is called monotonic. So I want to be super clear about that. Monotonic means either increasing or decreasing. Obviously, a function cannot be both, or a sequence cannot be both increasing and decreasing. So monotonic just means it's one or the other. You might not know which, but it's one or the other. All right. So example 10, is a sub n equal to n over n squared plus 1, increasing, decreasing, or not monotonic? Now, there are a few approaches to use for this. Generally, what I prefer students to do is try to make a direct algebraic comparison between a sub n and a sub n plus 1. So what I'm trying to get to is a statement that looks like a sub n is greater than a sub n plus 1, or a sub n is less than a sub n plus 1. But I don't know which it is. So what I'm going to do is just put a circle in between as a placeholder for my inequality. And I'm going to write out my formulas for each. N over n squared plus 1. And this will be n plus 1 over n plus 1 squared plus 1, right? The n plus 1th term is just what I get when I plug n plus 1 into the formula in place of n. And now I'm going to do some algebra to rearrange this until I get it to a form where I can tell if it's larger or smaller. So I'm going to multiply the denominators of each one across. Now, one thing you have to be careful about here is that when you're multiplying denominators across an inequality, if the denominator was negative, it would switch the sign of the inequality. But in this case, all of these terms are positive, so we don't have to worry about that. So no flipping inequalities on this one. Let's multiply this stuff out. We get n squared plus 2n plus 1 plus 1. That's n squared plus 2n plus 2. Compared to, and then when I multiply this out, I get n times n squared is n cubed plus n, 1 times n squared, plus 1 times 1 is 1. That gives me n cubed plus 2n squared plus 2 compared to n cubed plus n squared plus n plus 1. I just changed the order of the terms there. And now I can subtract n cubed from both sides. And what else can I do? I can subtract an n squared term. Oh, that's supposed to be a 2n. n times 2 is 2n. Oops. I can subtract an n squared and an n. And when I do that, I'll get n squared plus n compared to 1. And I know that as long as n is greater than or equal to 1, I'm going to get a bigger number here. This is an increasing function, so this is bigger than 1. So since I know my inequality wouldn't have flipped during any of my steps, I can just go back through and fill in those details. So since a sub n is greater than a sub n plus 1, or a sub n is less than a sub n, or a sub n plus 1 is less than a sub n, that implies that the sequence is decreasing. Now, of course, we know from Calculus 1 that we can often take derivatives to compute and show a derivative is positive or negative to show that something is increasing or decreasing, but there's a little problem with sequences, and that's why I really want students to focus on practicing on this algebraic approach. So we'll just draw a little bit of an aside here. You could always have a sequence that's decreasing like this, but it's the function that it's related to, the real valued function, might do something like this. So you've got a sequence that's actually decreasing, but the function that you would use to compare it to doesn't actually decrease, just because of where the sequence terms line up with that function. So you can't always use the related function because they won't always be strictly increasing or decreasing. So we want to practice this algebraic skill so that we have that when we need it. Okay, with that in mind, let's tackle another example. Is a sub n equal to 2n minus 3 over 3n plus 4, increasing, decreasing, or not monotonic? And again, I'm going to look at comparing the two terms a sub n and a sub n plus 1. So I'm comparing 2n minus 3 over 3n plus 4 to 2 times n plus 1 minus 3 over 3 times n plus 1 plus 4. And now I'm going to multiply my denominators across, but I'm going to do a little simplifying while I'm at it. 2n plus 1 minus 3 works out to 2n minus 1. And when I multiply this denominator across to the left, I get 3n plus 3 plus 4. That's 3n plus 7. And over here, I multiply by 3n plus 4. All right, let's distribute all this out here. We get 6n squared minus 9n plus 14n. That's plus 5n minus 21, compared to 6n squared minus 3n plus 8n. That's plus 5n minus 4. And so 6n squareds are going to cancel, 5n is going to cancel 5n, and now we can just compare negative 21 and negative 4. And of course, negative 4 is bigger than negative 21, so we'll carry that back through, and we see a sub n plus 1 is bigger than a sub n, so this implies a sub n is an increasing sequence. All right. So example 12 is a sub n equal to e to the n over n, increasing, decreasing, or not monotonic. Now, this one is the kind of situation that I described a few moments ago, where I can turn to a related function, a related real valued function, and use properties from calculus 1 and derivatives to determine if it's increasing or decreasing. So let f of x be e to the x over x. Then f prime of x is, all right, this is a quotient, so we have to apply the quotient rule. Get the derivative of the top times the denominator minus the top times the derivative of the denominator, all over the denominator squared. Factor my numerator, I get e to the x times x minus 1 over x squared. And what do we see? E to the x is always positive, x squared is always positive, and x minus 1 is positive as long as x is greater than or equal to 1. And since we're talking about a sequence here, that implies that it will be totally fine, because whenever x is greater than or equal to 1 is going to line up when n is greater than or equal to 1. So, since f prime is positive, that implies f is strictly increasing, and that implies a sub n equal to e to the n over n is increasing as well. Okay, moving on. Got a few more definitions here. A definition: a sequence a sub n is bounded above if there is a number m such that a sub n is less than or equal to m for all n greater than or equal to 1. So all this says is, if I've got my sequence of terms and there's some number up here m where none of the terms ever go above that number, it's bounded above. And a sequence is bounded below if there's a number little m such that all of the terms of the sequence are above that number. If a sequence is bounded both above and below, that being the key word here, both above and below, then it is called a bounded sequence. So in other words, if I have a sequence where I have some upper bound cap m and lower bound little m, and the sequence terms are always stuck between those two things, we call that a bounded sequence. So a sequence can be bounded above or bounded below, or it can be both, and then it's a bounded sequence. So example 13 says, or asks, is the sequence a sub n equal to 2n minus 3 over 3n plus 4 bounded? Well, what we know from our previous problem was that, so example number 11, we showed that this sequence was increasing. So we already know that a sub n is increasing. And if a sequence is increasing, that means every term is bigger than the first term, which means all of the terms in this case are bigger than what we get when we plug in 1, which is negative 1 over 7. What else it tells us is that if the sequence is increasing, it also implies that the terms of the sequence are all smaller or equal to the limit as n goes to infinity of those terms. So if we can compute that limit, we'd have an upper bound on this thing. And of course we can compute that limit. This is that very standard kind of algebra limit where I multiply by 1 over that highest power of the denominator, and I get the limit as n goes to infinity of 2 minus 3 over n over 3 plus 4 over n, which is 2/3. So altogether, that tells me that all of the terms of the sequence are bounded by negative 1/7. That should be greater than or equal to. And all of them are bounded above by 2/3, which implies the sequence itself is bounded. Okay. That's it for that one. Now we have one more theorem, and then one example applying said theorem. The monotonic sequence theorem. Now the statement of this theorem is really, really simple. If a sequence is both bounded and monotonic, then it is convergent. So what that means is if I have an upper bound and a lower bound, and the sequence just keeps going, say, up or going down. It just keeps increasing. At some point, it's going to have to hit a limit. The limit may be m, or it may not be m. But at some point, if that sequence keeps increasing, but it has an upper bound, it's got to stop. It has to find a point that it doesn't go past, and that point is the limit of the sequence. So, how do we prove this? Well, it's a little bit tough to prove. We have to use our formal definition for the limit. So we're going to go through that proof, but we're just going to go through the upper bound version rather than the lower bound version. So we'll basically, you rewrite the proof the same way, but you change the terminology and flip a few things around. So we'll just deal with considering when the sequence is bounded above, it's going to be bounded on both sides, is increasing. We're just looking at the case where it's increasing first, and then decreasing is almost the same proof. So, suppose that our sequence a sub n is increasing. Since the sequence is bounded, that's one of our conditions, the set S of terms for a sub n has an upper bound. Right? What that means is it's bounded, it's got some upper bound, m or l or whatever. Now, since the real number line is complete, meaning there's no gaps between numbers, there has to be some number that's the smallest upper bound, the least upper bound. And so since there is a least upper bound to this set, that means for any number, any positive number, epsilon, L minus epsilon is not an upper bound for S. Because again, L is the smallest upper bound, so if I take a number away from that L, I have a smaller number, it's not an upper bound anymore. Now, since L minus epsilon is not an upper bound, there must be an integer n such that the term a sub n is bigger than L minus epsilon. But this sequence is increasing, so all of the terms past cap n will be bigger than L minus epsilon. So we get, for any n greater than cap n, a sub n is greater than L minus epsilon, and therefore, if I subtract a sub n and add epsilon to the other side, we get that L minus a sub n is between 0 and epsilon. But this is quite literally the definition of the limit. So in conclusion, the absolute value of L minus a sub n is less than epsilon, and by definition, the limit as n goes to infinity of a sub n is L. Again, the proof when a sub n is decreasing is similar, but we talk about greatest lower bounds instead. Okay, so let's try to put that to use. And this is going to be a pretty challenging problem to end on, but hopefully we will follow along. Show that the sequence defined by a1 equals 2 and a sub n plus 1 equals 1 over 3 minus an satisfies that all of the terms a sub n are between 0 and 2, not including 0, but strictly including 2, and is decreasing. Show that the sequence is convergent and find its limit. Okay, so how am I going to show that the sequence is convergent? Well, the convergent part is relatively easy because I know if a sequence is increasing or decreasing and bounded, it's convergent. That's the monotonic sequence theorem that we just discussed. So if I can show that this thing is decreasing and I show that the terms are between 0 and 2, I can apply the monotonic sequence theorem and show that this thing converges. Okay, so the tricky part is how to show both of those things. But in this case, we can actually show both at once. So really, we want to show that a sub n plus 1 is less than a sub n, which is less than or equal to 2, but also is positive. So all of the terms are between 0 and 2, and each subsequent term is smaller than the one before it. So we're going to do what's called a proof by induction. And basically, proof by induction works like this. You show that something is true for one specific value of n, and then you assume that it's true for some general n to show that it's true for n plus 1. So essentially what it's like saying is, hey, I proved it's true for 1, and I proved that if it's true for n equals 1, it must be true for the next term. Therefore, it's true for 2. But it also must be true for the next term. Therefore, it's true for 3, and so forth and so on. So essentially, we're writing an algorithm to show that for any n value, if it's true for that n value, it's also true for the next one. So first we'll look at n equals 1. So when n equals 1, we've got a1 is 2, and a sub 2 is 1 over 3 minus a1, which is 1 over 3 minus 2. That's 1 over 1, which is 1. And so what did that show? Well, a sub 2 is in fact less than a1, which is less than or equal to 2 and greater than 0. So we just showed that when n equals 1, this is true. So now we assume it is true for n and show it will therefore be true for n plus 1. Okay, so since it's true for n, we have some a sub n plus 1. It's less than a sub n. It's less than or equal to 2 and greater than 0. Of course, that means that a sub n is bigger than a sub n plus 1. But if I multiply both sides by -1, I get negative a sub n plus 1 is less than negative a sub n. And if I add 3 to both sides, I get 3 minus a sub n plus 1 is less than 3 minus a sub n. And now if I flip them, so I take the reciprocal 1 over these, that also flips the inequality around. And so that gives me 1 over 3 minus a sub n plus 1 is greater than... Oh, wait a second, hold on. I didn't flip my inequality when I made these negative, so that's all messed up. Let's try that again. When I multiplied by -1, my inequality needed to flip. And now, since I am taking the reciprocal of both sides, that also flips our inequality. Like, for example, if 5 is greater than 3, 1/5 is smaller than 1/3. So 1 over 3 minus a sub n plus 1 is less than 1 over 3 minus a sub n. But what are these two things? So I'm going to just move this down here for space. So this expression here is a sub n plus 2. And this expression here is a sub n plus 1. Now we already know that a sub n plus 1 is less than or equal to 2. And we also know that a sub n plus 1 is positive and less than 2. So 1 over 3 minus that is also positive. So this is greater than 0. And so we showed that a sub n plus 2 is less than a sub n plus 1 less than or equal to 2. So in other words, we used the fact that we had a sub n plus 1 less than a sub n to show that a sub n plus 2 was less than a sub n plus 1. Equivalently, we're saying, hey, a2 is less than a1, and we're using that to show a3 is less than a2. And then we can use that to show a4 is less than a3. So what we've done is written an algorithm that shows each term bounded by the term before it and still positive. And that proves it for the n plus 1 case. Now, proof by induction is a pretty tricky idea, and you won't have to do a whole lot of that in this class, but I did want you to get some exposure to the idea here. Now, what does that do for us? That shows that the sequence a sub m is bounded and decreasing, which implies convergence by the monotonic sequence theorem. Now that truly is the hard part of the problem, but the question also asks us to figure out what the limit is. So it asks us to evaluate the limit of the sequence, but that's pretty tricky. So we want the limit as n goes to infinity of a sub n, but we know that this has to be the same as the limit as n goes to infinity of a sub n plus 1. Starting one term higher doesn't mean we end up at a different place. It just means we're starting at a term higher. So what does that look like? Well, a sub n plus 1 is 1 over 3 minus a sub n. And so what do we have here? If this limit as n goes to infinity of a sub n is L, then when I take this limit, this should be 1 over 3 minus L. So what that gives us as an equation, that L would have to be equal to 1 over 3 minus L. So I multiply the 3 minus L across. I get 3L minus L squared equals 1. I'll add the L squared and subtract the 3L. That gives me 0 equals L squared minus 3L plus 1. And if I factor that, I get L. Let's see, that is not trivial to factor. So instead, we'll just use the quadratic formula. So L is negative 3, that's 3, plus or minus the square root of. That's negative 3 squared, that's 9, minus 4 times 1 times 1, over 2a, 2 times 1. That's 3 plus or minus the square root of 5 over 2. But L has to be less than or equal to 2. And so if I look at 3 plus the square root of 5 over 2, that's going to be too large. So that implies that L is 3 minus the square root of 5 over 2. Okay, that was a real challenging problem. A real brain twister. All right. Well, that's the end of this video. Thanks for watching.